Hello everyone, my name is Mujtaba Alhadi and I will be presenting on the evolution of operating system architectures in the era of multi-core processors. Today we are going to look at how the shift from single processor to multi-core chips forced a complete rethink of how we design the software that manages our computers. To understand the problem, we first need to look at history. For decades, software developers enjoyed a free lunch. If your software was slow, you just waited for a faster processor. This was the era of frequency scaling. However, around the mid 2000s, this stopped. We hit a physical power wall known as the breakdown of linear scaling. We couldn't make processors faster without them melting. So manufacturers changed strategies. Instead of one fast brain, they started putting multiple brains or cores on a single chip. This solved the hardware problem, but it created a massive problem for the operating system. The monolithic challenge. The issue was that our most popular operating systems like Linux and Windows were designed for a different era. They are monolithic, meaning the operating system is one giant program where everything shares the same memory. In the early days, Linux handled multiple processors using something called the big kernel lock. This was a safety mechanism that only allowed one core to execute operating system code at a time. Imagine a four-lane highway where only one car is allowed to drive at a time. It completely wasted the potential of the new hardware. The cost of sharing. Even after engineers spent years removing the big kernel lock, they ran into a physical problem, the cost of sharing memory. Modern CPUs use local caches to run fast, when multiple cores try to read and write the same data. When multiple cores try to read and write the same data, the hardware has to send messages back and forth to keep those caches updated. This is called cache coherence traffic. It gets so bad that we sometimes see negative scaling. This means that adding more cores to a machine can actually make it run slower than before because the system spends all its time managing logs instead of doing work. Evolution 1. Refining the monolith. So how did Linux survive? Developers implemented massive optimizations to save the monolithic model. First, they moved to fine-grained locking. Instead of one lock for the whole operating system, they created thousands of tiny locks for specific data. This allows more cores to work in parallel. Second, they introduced RCU, Ready Copy Update. This allows cores to read data without locking it at all. If a core needs to write, it makes a copy first. This was a game changer for performance. And finally, modern operating systems are now NUMA aware. They try to keep problem running on the same chip where its memory is stored, avoiding the delay of crossing the motherboard to fetch data. The multi-kernel barrelfish. While Linux evolved, researchers argued that we needed a radical new design. One such design is the multi-kernel, also known as barrelfish. Barrelfish argues that a multi-core computer isn't just one computer. It is a distributed network of cores. Instead of sharing memory and fighting over logs, cores in Barrelfish send messages to each other exactly like computers sending emails across a network. This reduces cache traffic and allows the operating system to scale to hundreds of cores easily. Another radical approach is the factored operating system, or FOS. Traditional systems use time sharing, where every core does a little bit of everything: network, disk, application code. This fills up the CPU cache with junk. For FOS proposes space sharing. It dedicates specific cores to specific jobs. You might have one core that only handles network, uh, another that only handles the file system. This keeps the CPU caches hot with the right data, improving the efficiency. The modern solution: kernel bypass. In modern data centers, we have a new problem. The network is too fast with 100 gigabits Ethernet. The operating system itself is the bottleneck. The solution is kernel bypass, used in systems like Arrakis. Here we split the operating system. The operating system sets up security, but then it steps out of the way. The application is allowed to talk directly to the hardware. This removes the operating system from the critical path, uh, and this lowers the latency. Finally, we are seeing specialized scheduling. For data centers, systems like Shinjuku see hardware interrupts to switch tasks thousands of times per second. This ensures that short, important requests don't get stuck behind long, slow computations. On the mobile side, we have energy-aware scheduling, EAS. Phones use ARM big dot little chips, which have powerful cores and efficient cores. EAS doesn't just look for an empty core, it looks for the most efficient core for the specific task for the specific task to save your battery. In conclusion, the era of the one-size-fits-all operating system is fading. General purpose systems like Linux have successfully adapted using fine-grained logs and RCU. However, for high-performance needs, we are moving toward specialized designs, whether that means treating the computer like a network, as seen in Barrelfish, or bypassing the kernel entirely, as seen in Arrakis. The future of operating system architecture is about explicitly managing the complex relationship between software concurrency and hardware parallelism. And that's it. Thank you for your time.